Hi, we are Group 6 and today we are looking after the industrial process of one of the most important substances in human history, as it is the sulfuric acid. This sulfuric acid is used by economists to judge the industrial strength of a nation. But the real question is how can we make this on a massive scale? And this sounds like a very silly question but have a lot of process behind. The process we use to produce sulfuric acid is the contact process that consists in 5 steps. These 3 and these 2. But this process have perfection in the 20th century as we can see here. This also produced a fight between thermodynamics and kinetics that engineers need to solve in order to produce sulfuric acid. And now we go on to the first step, that is the production of sulfur dioxide, as we can see in this slide. Sulfur dioxide can be produced by burning sulfur or also by burning sulfur by containing ores such as iron, zinc, or galena. Sulfur dioxide can also be produced by burning hydrogen sulfide in crude oil. And here in this picture we can see all the equations that give us sulfur dioxide.
Okay, so now stage 2, which is the oxidation from sulfur dioxide to sulfur trioxide. So the sulfur dioxide is mixed with air and passed through a purification chamber to remove dust particles and other impurities. These impurities could render the catalyst use, meaning that they could poison the catalyst. Then these gases are dried, and these purified gases are then heated to a temperature of 450 to 500 degrees Celsius and compressed over heated vanadium oxide catalyst. Under these conditions, the sulfur dioxide is converted, is oxidized to sulfur trioxide. So this specific step represents the classic battle, as seen here, between the conflict between thermodynamics and kinetics. So this reaction is reversible and exothermic, meaning that it releases heat. So the part of the yield, which contains the thermodynamics in this case, tells us that according to the Le Chatelier's principle, which we've already seen, because the reaction releases heat, lowering the temperature would shift the equilibrium to the right, meaning that a low temperature is theoretically best to get the maximum amount of sulfur trioxide, which is the yielding part. And the kinetic part is the speed at which this reaction occurs, because these particles move slower when they are cold. So if we run this process at a low temperature to get a high yield, the reaction would be slow and it would take years to fill a tank. So to increase the rate of reaction, we need a high temperature so that the speed goes, faster. So the compromise here is that engineers solve this by choosing a compromise temperature of 450 degrees Celsius, because this is high enough for the reaction to happen quickly, and it is low enough for the equilibrium so that the equilibrium doesn't shift too far back to the reactants. So to make this compromise work, we rely on the vanadium oxide catalyst. So this catalyst lowers the activation energy, allowing the reaction to proceed fast enough at this lower temperature without needing to turn up the heat to ruin the yield. So this reaction is exothermic, and the temperature rises to about 600 degrees Celsius. And under these optimum conditions, there is a 98% yield of sulfur trioxide.
Stage 3. The production of oleum. This stage it will call the absorption tower. This is where the gas is gonna become a liquid. But this is a delicate operation requiring a precise engineering. First, the hot sulfur trioxide gas leaving the converter is passed through a heat exchanger to cool it down. If it enters the tower too hot, it will damage the equipment. Once cooled, it is pumped into the bottom of a massive steel tower lined with acid-resistant brick. The design. Inside, the tower uses a counter-current flow system. The gas is pumped in at the bottom and rises up, while a stream of concentrated sulfuric acid is sprayed from the top and trickles down. To ensure they mix perfectly, the tower is packed with thousands of inner ceramic rings. These rings force the liquid and gas to take a winding path, drastically increasing the surface area and contact the time between them. The safety critical warning. Now you might ask, why not just spray water? We want to make acid, and acid is SO3 plus water, right? In theory, yeah, but in practice, this is disastrous. The reaction between SO3 and liquid water is violent exothermic. It releases so much heat so quickly that it instantly boils the water into steam. The SO3 then reacts with the steam to form a stable aerosol, a fog of microscopic sulfuric acid droplets. This acid mist is incredibly difficult to condense back into liquid. It's very difficult. If formed, it will float right out of the factory chimneys, creating a toxic cloud that destroys local vegetation and damages lungs. The result of this problem is quite simple. To prevent this, we use the acid to make acid method. The liquid trickling down the tower is actually more or less 98% concentrated sulfuric acid, and because it contains very little free water, the SO3 gas dissolves into it smoothly without the violent boiling. Finally, the result of this experiment, as the SO3 is absorbed, it chemically combines with the acid from a thick, heavy and oily liquid called oleum, H2S2O7, also known as fuming sulfuric acid. It's called fuming because if you open a jar of it, SO3 gas escapes and reacts with moisture in the air to create white fumes. This oleum is essentially a super concentrated storage form of the acid. It flows out of the bottom of the tower, safe, stable, and ready for the final dilution step, for the stage 4.
Stage 4. Dilution of oleum to form sulfuric acid. Oleum produced in stage 3 is mixed with a carefully calculated quantity of water to give concentrated sulfuric acid. The acid obtained from this process is about 98% pure. About half of this goes directly into making fertilizers, like ammonium sulfate, which helps feed the world. The rest is used to clean steel, refine oil, and act as an electrolyte in your car battery. Now we're going to talk about the applications of H2SO4. The vast majority, about 50% of the global production, goes directly into agriculture. It is used to solubilize phosphate rocks to create superphosphate fertilizers and ammonium sulfate, which are essential for feeding the world's growing population. Beyond farming, it is the workhorse of the chemical industry. We use it to manufacture detergents, synthetic fibers like rayon, and even paints and pigments like titanium dioxide. In the metal industry, before steel can be galvanized or plated for your car or appliances, it must be cleaned of rust. This process, called pickling, uses huge baths of sulfuric acid. Finally, it plays a critical role in energy. It is used to refine high-octane gasoline in the petroleum industry, and of course, it is the electrolyte liquid inside the lead-acid battery that starts your car every morning. To summarize, we burn sulfur to get sulfur dioxide, oxidize it over vanadium catalyst to get sulfur trioxide, balancing heat and speed, and then absorb it into acid to safely produce the final product. This is the contact process, a triumph of chemical engineering. These are the references we used, and thanks for watching.